I'm going to continue this story but it's going to get more advanced. So the prerequisites at this point are some linear algebra, and in particular the idea of eigenvalues and eigenvectors and diagonalizing a matrix and using that to take powers of a matrix. And this is a really great way to analyze Fibonacci and other recursions, recursively defined sequences, even if you have no interest in um, this connection to sines and cosines, but it particularly explains what's going on in this setting. So if you've taken like a standard differential equations and linear algebra course, that's a perfect prerequisite. Okay, so the question I'm asking here is, why does this work? Is there some meaning to this that's deeper? And usually in mathematics, a good way to find the meaning for something is to generalize. Is this something that's a general phenomenon that happens more than just in one case? And why did we have to twist? What was going on with that? And there's various ways to explain that. So let's go into a more general setting, the idea of a general Lucas sequence. So when we've got L sub n, that's a very particular sequence, but there's an idea of a general Lucas sequence, and that's just any sequence that satisfies a two-term recursion, a linear two-term recursion, and usually you require p and q here in the recursion to be integers so that you actually get integer sequences. But again, that's not super important for the point of view that I'm taking, which is very not number theoretical, really. It's more analytic. So there's a minus sign here, a conventional minus sign. We'll see why it's good to think of this this as minus q times a sub n. So Fibonacci is just where p is 1 and q is minus 1. So remember that. Okay. So here's what we're going to do. A very standard thing to do is it's a little annoying that you're creating this new one number, an plus 1, but you have to remember two numbers in order to do it. And that's asymmetrical, that you use two pieces of information to create one. So the clever trick is you actually think of the object that's being created at each stage as a pair of numbers, the new number, and you just automatically put in with that the previous number as just for bookkeeping purposes. And we make that a vector. It's a nice vector in the plane. Okay, so what does this rule translate to in terms of the vectors? It says Vn plus 1. Okay, that's just going to be An plus 1 An, just increment each of the indices. Now the rule says An plus 1 is determined by An and An minus 1. Okay, well, all of the information here is exactly what is contained in the previous version of the vector, and that's the payoff here, is that this vector has exactly got the information we want. Okay, now a sub n is very easy. That's just the old top component. So we shuffle down the top component and demote it to be the bottom component, because that just says, okay, that's now the old one. What was the new term in the sequence is now the old term in the sequence. So that just gets shuttled down here. In terms of matrices, that just says that I'm going to multiply the old vector, which was the old new guy and the old guy, and I'm going to multiply that by a 1, 0 on the bottom row, which just takes what was the top row and turns it into the bottom row. It's exactly what you should think of when you see a matrix, 2 by 2 matrix with a 1, 0 on the bottom. It just takes the old top entry of a vector and turns it into the new bottom entry. And then the interesting action goes on the top, that p times an minus q times an minus 1 gives you the new an plus 1. Okay, so what we see now is that this is very nice expressed in terms of matrices. I have a sequence of vectors, two-component vectors, and I just repeatedly multiply by this fixed matrix with integer entries. Okay, and this also, remember, the initial data you need for any one of these sequences is two numbers, and that makes sense because we're taking a vector like v sub 1, for example, will be a sub 1, a sub 0. You need all that information to get started. You can't just seed it with a single number. Okay, so this is a very nice perspective, and this is how a lot of people think about these guys, is they're really matrix recursions, and of a special type, where this bottom row is a very specific set of numbers, 1, 0. Okay, so to create something out, okay, so let's just let this be A. Let's abbreviate that as A. And so we take our seed, let's say V1 is going to be A1, A0, and we just apply powers of A. So this makes it formally look trivial. It's like, oh, that's all there is to Fibonacci and all these generalizations? You're just taking a vector and then multiplying it by powers of a matrix. Well, what that tells you is that there's a lot to the idea of taking powers of a matrix, that's actually pretty, can give you interesting and maybe unexpected results. But that really is a very powerful way to think about it. It's like, oh, really? That's cool. If you've never seen that, hopefully that's pretty exciting. Okay, now, how do you take powers of a matrix? Well, the clever way to do that, or one of the best clever ways to do it, is to diagonalize it using eigenvalues and eigenvectors. Okay, so let's run through that. This is where you definitely need to have seen this before because I'm not going to sort of give a course on it. So to find the eigenvalues, very common way is look at the characteristic polynomial. You take the determinant of a minus lambda I. There's a minus lambda I right there. The determinant of that, if you want to pause and calculate that, is just lambda squared minus p lambda plus q equals 0. Very nice simple quadratic. Here's the solutions. P plus or minus root p squared minus 4q over 2. And I'm just going to have a notation for that. One of those eigenvalues with the plus is going to be, I'm going to call it alpha, and the other eigenvalue I'm going to call beta, that's the one with the minus. And sometimes the discriminant comes up, it comes up enough that we would like a notation for it, and d is a pretty obvious one. So we're going to abbreviate that as d, so p squared minus 4q. So some things to remember that's always true in this case about the eigenvalues, three equations that are very useful to remember, is the sum of the eigenvalues, and this is a very general thing about the eigenvalues of a matrix, they sum to the trace of the matrix. And the trace is just by definition the sum of the diagonal entries. So they sum to p, and if you don't believe that, just add these two numbers, it's pretty clear. The product of the two eigenvalues of a 2 by 2 matrix is always the determinant of A, and that's going to come back to us pretty soon. That is Q here, and that's the big reason why we had the artificial, what seemed like a weird artificial minus sign. It's so that the determinant of this guy, which is a really important thing about a matrix, is just going to be Q. So P times 0 minus Q times 1 gives you Q. Okay. And again, if you take the product of these and expand it out and put in the definition of D, you'll see that's Q as well. And a somewhat less important is that the difference between alpha minus beta, that does show up pretty soon, is just root D, pretty obvious. Okay, so these are sort of the three things you must remember about alpha and beta to make all this make sense. Okay, so let's go back to the case we're familiar with, Fibonacci and the usual Lucas sequence. That's where P is 1, Q is minus 1. So D, it's easy to show that that's 5. Alpha is the golden ratio. There it is expressed. We've seen that before. And beta is the conjugate of the golden ratio, and that's often called psi. Okay. So that's a very standard case. And so whenever you're looking at this stuff as I go through this, if you want to make it a little bit more familiar, just look at this case and let alpha be the golden ratio and beta be the conjugate golden ratio. Now, there's a bit of an annoyance here. If d equals 0, you get a double root. That's always special. You don't get two distinct eigenvalues. You can't diagonalize the matrix, all kinds of stuff. Very, very important in the story of linear algebra, but wonderful to ignore when you can, and I get to decide these things in this video, so we're going to ignore the case for d equals 0. So if anything looks suspicious, it might be because we're assuming d is not equal to 0 throughout. So we're not done with the diagonalization story in general. We need the eigenvectors. Okay, how do you do that? Well, the eigenvector corresponding to alpha, it's called v sub alpha, is just the solution of this equation. A minus alpha I should kill that vector. I put in that, I make that explicit, and then the nice thing, remember, if you've done this, about finding eigenvectors for a 2 by 2 matrix, you don't have to do a lot of work to solve this. We know that this is a dependent system of equations, or else there won't be a non-zero solution. And so you just have to solve one of the equations. And 1 minus alpha, all you have to do is switch the order of these guys and switch a minus sign. So alpha 1 will work. That's obvious that this times this dies. It's not as obvious that this times this dies, and you have to actually expand things out and make sure it works. But it should, and it does. It's guaranteed to work if we did the eigenvalue calculation correctly, and we did. Okay, the other eigenvalue corresponding to beta, or the other eigenvector corresponding to eigenvalue beta, is just beta 1, really easily. Okay, so here's the punchline. We make those into a matrix, call it P, fairly standard name, but there's lots of other names. P inverse is going to be useful as well. It's easy to calculate that using the usual formula for an inverse. And the punchline is that we've expressed our matrix A which a priori would be hard to take powers of, as a matrix that's of the form P times a diagonal matrix times P inverse. In other words, we've found a similarity transformation, that's the terminology, between this very simple matrix, in particular something that's really easy to multiply it by itself repeatedly, and A. And when you take powers of A of this quantity, you stack these guys next to each other, you get a lot of P and P inverses canceling out. There's only one P that doesn't cancel out on the left, one P inverse that doesn't cancel out on the right, and on the inside you just get powers of this diagonal matrix, and that's easy. So again, I'm going through that kind of quickly because hopefully it's at least somewhat familiar. And if it's not, go find a reference on it. It's wonderful stuff. Okay. So what is that explicitly? Okay. Good exercise. If you multiply this matrix times alpha to the n, beta to the n times this matrix, it's a pretty easy exercise in matrix multiplication. You get the scalar coming out, 1 over alpha minus beta. So I told you we were going to see that number, alpha minus beta. And then it's pretty easy to show that you get this stuff in the middle. Okay, so this is the punchline for Lucas sequences, is that this is our master manipulating matrix. This, multiplied by any two seed numbers as a vector on the right, will give you the sequence of vectors, and then just pick out either one of the components of those vectors to get the sequence. So let's do that in the case where the initial vector is just 0. It's just 1, 0. In other words, the sequence at 0 is 0, and the sequence at 1 is 1, just like for Fibonacci. What happens when you take a matrix and multiply it by 1, 0? You're just picking out the first column of the matrix. Don't forget the scalar factor. So you just get this. Oh, and it's a to the n minus 1. Why was that? It's because, unlike in our usual, where was that? Unlike in our usual, I usually like to use the mathematician convention that I start counting at 0, but it just works better to start counting at 1 here, and that means I only needed to take n minus 1 steps to go from 1 to n. It's not a big deal. So we'll go back down to here. Okay. Okay, so a to the n minus 1 times 1, 0 just gives you the first column of this matrix with n minus 1 put in, and there it is. And what was that? Oh yeah, that was just a sub n and a sub n minus 1. So ignore this because that's just for bookkeeping. It's a good double check. This should be exactly the same as this with n minus 1 put in, and it is. And so here it is. A sub n is eigenvalue to the n minus other eigenvalue to the n over difference of the eigenvalues. That's a very famous result in the theory of Lucas sequences, and in particular for Fibonacci, this is Binet's formula. It is not the only way to get Binet's formula. It's not the simplest way to think about Binet's formula, but it's a very powerful way, and it connects with linear algebra, dynamical systems, differential equations, all kinds of good stuff. Okay, so that's a totally alternate derivation of Binet's formula from the funky one we had with cosines and sines. Okay. So this is what happens with the simplest initial condition. Okay. You could also, it seems like a reasonable thing to me to look at, well, what if you switched it? What if you say, instead of going for 0, 1, etc., 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 what if you went 1, 0, etc., etc., etc.? It just doesn't work into the theory quite as well, and we'll see some reasons for that. The other thing you usually do, as well as this guy, so we're gonna call this u sub n because it's special. Okay, that's the usual name, and capital U. That's different from my little u and little v. You can also look at the simplest in terms of the eigenvalues. Like, okay, this is a nice combination of alphas and betas, and what's really significant about it, of course, is that alpha and beta usually are not integers. They're not rational numbers. They have like golden ratio type stuff for Fibonacci. But this combination is guaranteed to be exactly just what you get by starting with 1, 0 and doing integer recurrence. That's guaranteed to be an integer. So surprisingly enough, this is going to be guaranteed to be an integer. Similarly, what's the simplest possible combination of these eigenvalues that you can put in that's guaranteed to be an integer? Well, it's alpha to the n plus beta to the n, because what does that start with? When n equals 0, you just get 1 plus 1 is 2. When n equals 1, you get alpha plus beta, and remember, one of the special things in this situation is that alpha plus beta, ooh, that's a p, just kidding. Alpha plus beta is going to be p, okay? I put that 1 there because in the Fibonacci case that's equal to 1. My mistake though. Okay. And so this is a funky thing. We've got these funky numbers that are coming from the quadratic formula. They're going to be quadratic irrationals. And you take the sum of one to the n and another to the n. Why is that working out to be an integer? It's because it's a clever analytic way to write the solution to something that has to be an integer. What happens if you start with 2 and the integer p, and then you run the recurrence that all has the integers p and q in it? Okay, so of course in the Fibonacci case, this is the Lucas sequence, not the generalized form. And that usually goes by the name of capital V sub n. Okay, so that's a very quick review, basically, or treatment of how you think of this in terms of matrices and get general answers. And we've got a very nice punchline. But I don't want us to forget the idea that, really this is coming from a matrix interpretation. It's a very nice way to think about it. Okay. Let me show you, let me get a little payoff for this, not just completely review standard stuff. So one of the questions again was, why did we need to twist F and L? The scaling is not super crucial here, but why did we need to twist them? We saw in the last video that that really makes a pretty picture with these spirals, but why was it necessary in order to find the connection between sine and cosine? Okay, so let's look at this analogy here. Now that we've got these formulas, there's a very nice analogy. In any general Lucas sequence situation, the un, which starts with 0, 1, one of the simplest cases, there's a sort of an analogy here. We've got something to the n minus something to the n over constant. Here's something to the z minus something to the z over constant. With v sub n, alpha to the n plus beta to the n, and I claim that's analogous to cosine. Now this has an over 2. That's basically because it's convenient when you're working with, when you want everything to be integers, to start this with 2, but cosine wants to start with 1. So again, it's a scaling factor. That's not super crucial. So hopefully it's a fairly clear analogy. Again, this is something you could look at and be like, hey, I think there's something going on here, even if you didn't know any of the other identities that we use to motivate this. But here's what's special about on the right-hand side. E to the I to the z is how I wrote it, and e to the minus I to the z. These two numbers are reciprocals of each other. This is e to the I, this is 1 over e to the I, similarly here. Okay, so that's not generally true over here. Alpha times beta is not generally equal to 1. Alpha times beta is equal to q in general. So this is only going to actually work if we've got a situation where q equals 1. And that's not true for Fibonacci and Lucas. What we did was we twisted them in order to actually create a new Lucas sequence that had q equals 1. So here, let me show you how to do that, and then we'll end this fairly long video. Okay, so in general, just take any number k, and we'll start with Fibonacci, and we can talk about the general Lucas sequence in a minute, but let's just start with Fibonacci like we did. And we want to create a new Lucas sequence that satisfies a different recursion that has q equals 1 instead of what we started with q equals minus 1. Okay, and the reason I'm multiplying it by k to the n minus 1 is so that when n equals 1, I don't mess with the initial condition. Okay, so this will still start with 0, 1, just because this started with 0, 1. And we're not going to worry about the scaling. Just the twisting is really the crucial thing. Okay, so what's the recursion relation for fn? It's this guy, and that's a plus, and we want to change that to a minus here, right? So what's the relationship for u going to be? Well, un plus 1 is, by definition, k to the n times fn plus 1. Okay, that's k to the n times fn plus k to the n fn minus 1, using the recursion relation for this sequence, which we are now looking at as not what we really want. And what is this? How is this expressed in terms of u sub n? Oh, okay, that's k times un plus k squared times un minus 1. So we've created a new sequence very closely related to fn. It's not hard to translate between them, and we've done that a lot in the last few videos, but where we've changed the recurrence, and in particular, we were able to change q from 1 to k squared. In this case, from minus 1 to minus k squared, because remember, this really wants to be written with a minus sign. What we really want is k squared is minus 1, and voila, that's why we had to twist with an I, with powers of I. So this is a very basic reason why we had to do that kind of twist. In general, suppose you start with any Lucas sequence instead of just the Fibonacci, and you twist it, you're going to change whatever the q is for your old sequence to kqk squared. You're also going to change the p to pk, which matters, but what's really more crucial is the q, and we'll see another reason for that next. Okay, so what happens, something I could have said before about like the little u sub n sequence that we've had in the videos, instead of having this recursion, this is really the recursion law that we've been dealing with. We've been really secretly dealing with a new Lucas sequence that has this recursion, and that turns out to be something of this form, a sine function. Okay, good place to stop this one.